Hello everyone, welcome to the lecture. Myself Devananda Rao, working as Associate Professor in the Department of CSC, MLR Institute of Technology, Hyderabad. Today's topic is issues in the design of a code generator. Code generation. The final phase in compiler model is the code generator. It takes as input an intermediate representation of the source program and produces as output an equivalent target program. The code generation techniques can be used whether or not an optimization phase occurs before code generation. Here, code generator is the last phase of the compiler. We have total 6 phases: lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, code optimizer and code generator. This is the last phase of the compiler. The input for code generator is the intermediate code, intermediate representation of the source program. The output is target program, that is machine code. Here, this diagram showing position of code generator. Here we have, before code generator we have code optimizer. Here code optimizer is optional. Code optimizer is optional. That is, code generation techniques can be used or applied whether or not an optimizing phase occurs before the code generation. See, front end takes source program as input, high level language source program as input and gives the intermediate code as output. Front end will take source program as input and gives intermediate code intermediate form as output. For that intermediate code, we can apply optimization techniques to improve the code. So, code optimizer is here optional. After that, we can give this intermediate code as input to the code generator. Front end and code generator will connected to the symbol table. Front end will maintain the symbol table. Both front end and back end, that is back end means code generator, front end and back end code generator will coordinately using the symbol table. Issues in the design of a code generator. The following issues arise during the code generation phase. First issue, input to the code generator. Second, target language, memory management, instruction selection, register allocation, choice of evaluation order. First issue is input to the code generator. It consists of the intermediate representation of the source program together with the information in the symbol table, that is used to determine runtime addresses of the data objects. Here, the front end will give the intermediate representation. That intermediate representation of the code is given to the target code as input. So, here the front end will also maintain a symbol table to store the names used in the source program, so that it will determine the addresses for the names in the source program for the entries for each entry in the symbol table represents the address for the names in the program. Next, intermediate representations may be 3 types: linear representation, 3 address representation, graphical representation. Linear representation is postfix notation, that is, for example, x star y is an expression. The postfix notation will be x y star, that is, operator comes after operands, operator appears after operands. Then 3 address representation. 3 address representations are quadruples, triples and indirect triples. See, 3 address statements are implemented by using 3 types, that is quadruples, triples and indirect triples. Quadruples having 4 fields, fold fields, that is, first field is operator field, then argument 1 field, argument 2 field and result field. Quadruples. Triples having 3 fields, OP field, that is operator field, argument 1 field, argument 2 field. There is no result field. Indirect triple is also a triple, but it gives indirect addresses, pointers to the triples. Next, graphical representation of the intermediate representation. Graphical representation is syntax tree or DAG. That is, for example, there is an expression x is equals to y star z. The syntax tree for this is y and z are evaluated first, So, that is assigned to x. This is syntax tree. Then DAG. DAG is also representing intermediate statement, that is 3 address statement. See, if you take a same x is equal to y star z, that is star is a interior node and left child is y, right child is z, and result is represented as a label to the interior node. This is DAG. So, input to the code generator is the intermediate representation. Intermediate representation may be linear representation, that is postfix notation, or 3 address representation, that is 3 address can be implemented as quadruples, triples, indirect triples, or graphical representation, syntax tree or DAG. Then target language. Target language. The output of the source, the output of the code generator is the target program. Target program may be 3 types. One is absolute machine language, another is relocatable machine language, last one is assembly language. The output of the code generation is 3 types, one of the 3 types: absolute machine language, relocatable machine language, assembly language. First one, absolute machine language. It can be placed in a fixed location of memory and immediately executed. That is, in absolute machine language, the output of the code generation is a code, target code. The instructions are in binary form, binary representation or hexadecimal representation, like this. So that these are understood by the processor, so that it can be immediately executed without relocatable. Second one, relocatable machine language. Relocatable machine language means here subprograms to be compiled separately. Here the program having different modules, each module is compiled separately, and a set of relocatable object modules can be linked together and loaded for execution by a linker. Here we need a linker to link all these modules and loaded to the memory. For example, relocatable machine language, we have 2 modules in the program. Module 1 having instructions, add instruction, R0, R1, R2. Here the content of R1 is added to R2, the result is stored in R0. So, for this, in the memory, the address for this statement is, for example, assume 1000. This is the address, relocatable address. 1004, we have another instruction, subtraction, sub instruction. R5, the contents of R4 are subtracted from R5, the result is stored in R3. And we have another module, module 2 having address 400, there we have instruction add R6, R7, R8, like that. These modules are combined together by the linker and loaded. While combining these modules, the addresses are adjusted. Then last one, assembly language. Code generation is made easier. That is, assembly language means uses mnemonics or symbols. Mnemonics and symbols to represent machine code instructions. It is more human readable and easier to work. For example, mnemonics, add R0, R1, R2. Contents of R1 are added to contents of R2, the result is stored in R0. This is the mnemonic assembly code. So that the output of the target code is assembly language, so that we need assembler. Assembler will convert assembly language program into target, that is machine language program. Then memory management. Mapping names in the source program to addresses of the data objects in runtime memory cooperatively by front end and the code generator. Here front end and code generator will cooperatively uses the memory, that is symbol table, mapping names in the source program. What are the names used in the source program? Those names are stored in the symbol table by using the addresses generated by the compiler. See here, the front end maintains a symbol table that stores information about variables, constants and functions and their attributes. Each entry in the symbol table corresponds to a name used in the source program. That means the front end generates 3 address statements that represents operations involving the names. For example, a name in the 3 address statements refer to a symbol table entry in the name. For example, we have names integer variables A, B, C are the 3 variables of type integer. So that these names for each and every name in the source program having entry in the symbol table, that is address, that will give the location to store the name content of the variables. So from the symbol table information, a relative address can be determined for the name in a data area of the procedure. For every procedure or function, a stack frame stack is assigned. There the names are stored. For example, we have a program like this, 3 variables A, B and C of type integer. A is 10, B is 20, C is equals to A plus B, return 0. So for this program, source program, the relative addresses for A, B, C variables are, so for this main program, a stack frame is assigned, stack frame is allocated. In the stack frame, offset address will be, that is a relative address or offset will be calculated for names A, B, C. So A is at offset, A is at offset 0, because A, B, C are integer variables. Each integer variable needs 4 bytes, 4 bytes of memory. So B is at offset 4 and C is at offset 8. That is, A is at offset 0 from base point, that is stack pointer, that is from stack pointer or base pointer. Like that, a relative address can be determined for the name in a data area. Data area means frame for a stack frame for the main, for the procedure. A name in the 3 address statement refers to a symbol table entry for the name. Next, instruction selection. The nature of the instruction set of the target machine determines the difficulty of the instruction selection. Here we have 2 types, simple instruction and complex instruction sets. Simple instruction sets, that is the length of the instruction are consistent, the format of the instructions are simple and the addressing modes are limited. Come to complex instruction set, the addressing modes are numerous addressing modes and different instruction lengths are available. So selection of instruction set is crucial for generating the target code. And uniformity and completeness of the instruction set are important. Uniformity means instructions might have consistent length and operand formats and addressing modes might follow a regular formats. Next, completeness of the instruction set are important. Completeness means the program having different operations, arithmetic operations, data movement and control flow, that is jumping from one location to other locations. These are the different operations. So if the instruction set provides all these operations, that instruction set is called completeness of the instruction set. So the instruction speed is also important while generating the target code. Say there is a instruction x is equal, there is an operation x is equal to y plus z. So the target machine code will be like this: move y comma r naught, that is the value of y is, content of y is moved to r naught. R naught is a register, move is a mnemonic, that is moving data from y to r naught. Y is stored in memory, r naught is a register. Next, add z comma r naught. Here z is a variable that is available stored in the memory. The content of z is added to the contents of register r naught. So now the result of addition is also stored in r naught. Finally, we can move the result from r naught to variable x. The quality of the generated code, is determined by its speed and size. The size should be less to increase the speed. For example, say a is equals to a plus 1. A is equals to a plus 1, that is 1 is added to variable a, that is increment of a. For this, the code, machine code, target code will be like this: move a comma R0, add 1 is added to R0, that is content of first instruction, content of A is moved to R0. R0 is a register contains the value of A. After that 1 is adding to the value of R0. So, the result is also stored in R0. Finally, move R0 comma A, the result is stored to move to variable A. So, 3 instructions are needed to perform this operation, just we increment one value of A. Instead of using these 3 instructions, if the target machine has an increment statement like this INC, we can use directly INCA, that is increment operation, increment instruction. It will increment the value of A by 1. Then register allocation. Instructions involving register operands are usually shorter and faster than those involving operands in memory. So, CPU can directly access the registers. So, if the value data, if the operands are available in the register, so that we can execute the program fastly. So that, but it is not possible to allocate registers for all the operands because the registers are limited in number. So that moving data from memory to registers, it takes time. So selecting the operands for allocating registers is playing a crucial role in the code generation. Efficient utilization of register is particularly important in code generation. The use of register is subdivided into 2 subproblems. First problem is, during register allocation, we select the set of variables that will reside in a register at a point in the program. In a program, if the variable are there, so we need to select those variables that are in register, that needs the registers. That is the first task. Second task is, after selecting the variables, because we cannot accommodate all the variables into a registers, because registers numbers are limited. So that after selecting some of the data variables, we need to select the, in the subsequent phase, we need to select the register, which register is used to store the variable. So this is register allocation. Then last one, choice of evaluation order. The order in which computations are performed can affect the efficiency of the target code. That is, some computations order requires fewer registers to hold intermediate results than others. For example, if you take any expression A plus B star C, evaluation order is very important. If you take one evaluation order, that is evaluate first B star C, that is added to A, that is one order. Another order, first perform addition of A and B and multiply with C. This is another order. Selecting order is also important because in order computation order requires few registers. Some computations require few registers than others. Thank you.